Hello again, everyone. So I want to keep this one quick. I just want to show stko or stk optimizers, what we have available, and just quickly how to use it. So it's available on the GitHub JAWS material group or through pip, although I would always recommend getting this one from the GitHub as it's constantly in development and the pip is a bit behind. Its requirements are basically the same as stk. So stko fundamentally provides a series of functions which take stk molecules or constructed molecules and spits out either a property or an optimized version of that molecule where the coordinates have changed. So I'm going to go through its capabilities and then some examples. So there are example scripts in this examples folder which I'll go through. So in terms of optimizers, we have 5, I guess, general groups. We have XTB, which uses the GFN XTB executable, which you have to provide, and can perform either an XTB optimization. You can see there's a lot of options here, so you can do a bunch of different things, and there's some examples of how to run it on a polymer, for example, where you use it as the final part of an optimizer sequence. So this will run whatever this UFF class is and then run this XTB class. So this handles the optimization process and it returns you your new molecule. All optimizers follow this process where you first define the optimizer and then you run new molecule equals optimizer.optimize old molecule. Cool. So I'm not going to run any of these examples because of their because they require XTB and so forth. So I just wanted to show that we have general XTB optimizers, and then we also have, if we go up, an implementation of the conformer search algorithm CREST and GFN, and we have an example of running that. And then the same thing but with the XTB force field, which is under development. It's very fast, but I've had structures that kind of result that don't work. So always use something like this carefully, because unlike STK, XTB does not use the bond topology within STK to define its molecule. It just uses the coordinates, so you're losing some information. We also have RDKit optimizers, so they're very simple. We have the ET-KDG conformer generation algorithm and the MMFF and UFF force fields. Trivial to use. They're not going to work on metal containing systems, but they will work on most organic systems of a reasonable size. We also have gulp, or a wrapper for gulp, which is useful for using UFF and UFF-MOF for metal containing systems. So I just have an example of doing that here. Again, this requires an installation of gulp, so I'm not going to run this, but this example should be all you need to do. One thing I'll note with this is that the force field assignment is done by RDKit and then manually overwrites the assignment of palladium or metal atoms based on what you provide it. And so this implementation may change in the future, as I found some issues with that assignment. Cool. We also have the collapser optimizers, which I would now say are left in there because to keep it backwards compatible, but these have been replaced with the MC Hammer code, and these are already implemented within STK as well, so I probably would not recommend using these. And then we have wrappers for Schrodinger's macro model, which is not free software. So again, this would also require the software, and I can't run these examples, but we show how to use that here. And this provides not only a force field optimization, but it also provides the, if I can click the link, no, it also provides the macro model MD process which runs molecular dynamics for a certain amount of time, extracts by default 50 conformers, optimizes all of them with macro model, and then gives you the lowest energy one. So that's its optimization through conformer search. And this is done at high temperatures to, explore the potential energy surface. Cool. stko also provides, currently limited but being expanded quite regularly, is the RD-kit and XTB calculators. But these, simply put, just provide the MMFF energy, and I'll show a usage of that later. And the XTB one can provide not only the energy but also other things that XTB produces, like the Fermi levels, the HOMO-LUMO gap, and so forth. Cool. One thing I wanted to show an example of is there's some other classes for handling molecular systems and I guess building upon the molecules of STK with other properties. For example, periodic systems, we can add the unit cell properties. We can look at a network X representation of an STK molecule with network material classes, or we can extract a topology. So I have an example for this in the examples code, topology extraction example. I will just copy this because I think it's interesting to run through. If we go to Jupyter Lab, we go here. Cool. So the first step is to build a cage. Let's just do this, and then I'll run through the pretend example at the end. So we need to obviously import things, and we go show stk mol cage 1. So let's pretend you were handed this cage and you wanted to build more like it, and so you wanted an STK topology graph to use for construction. Now you can see the long bonds which were used for the connection, and you would have to, in the real world, define these disconnected bonds manually. So you'd have to go in, find out their ID, and add them to this disconnectors list, or broken bonds by ID. So these are two lists which contain the atom IDs associated with this bond. So you can see it's that nitrogen and that carbon, for example, ID. But because this is a made-up example, we can just run this, which collects those atom IDs from the constructed molecule. So we now have, we can print those, already had that there. So we have the broken bonds by ID and the disconnectors. So disconnectors are it's a set of these atom IDs, whereas the broken bonds by IDs are the two atoms at either end of the bonds that are to be broken. Using the stko topology extractor, we can define a new topology graph. So we want to so we first define the topology extractor, which is a class. If I click this, does the inspector work? Extractor of a topology definitions for a molecule. Cool. So we define the class. We then extract this TG info by running extract topology, where we provide it the molecule, which is any STK molecule, and then these broken bonds by ID and the set of disconnectors. So we can run that. And now we can, for a TG info, so this returns, if we look at this extract topology class, I might actually just go to the code, because we're still working on all the documentations and so forth. So topology extractor, this topology extractor. So the topology extractor has this extract topology method, which returns a topology info. So a topology info is a class containing this information, and it contains the positions of separated building blocks, so disconnected building blocks, the connectivities of those building blocks, and the edge pairs, so what are connected. And it also has this write method so we can visualize it. So if we print, let's import os.make the tg output, and then let's change that. So we can print all of this information where the vertex positions are all you need to generate the idealized topology. The connectivities are what you need to figure out which vertex type you need. So for example, do you need a linear vertex or a non-linear vertex? And that's given here by the number. So this would require a linear vertex because it has 2 connections. This would require a non-linear vertex. And then the edge pairs allows you to generate the edges. So if we actually look at how a topology graph is defined in STK, STK, let's go to, I think I showed this in one of the earlier videos, but I'll show it again. Let's go to cage, pick 1, 2 plus 5, 12 plus 30, cool. So for every topology graph, you need to define the vertices. So here's a list of non-linear cage vertices, and they have their position, their ID, and their position, which is defined by some golden parameter. So this is the idealized geometry of all these 3, or I think they're 5 functional group building blocks or vertices. And then you append to that list all these linear vertices which are initialized at the center of their connected points. So the information provided here, which are the position of the vertices, the number of connections, and what they are connected to, allows you to quite quickly generate this idealized geometry. This is a very complicated one, as well as all of the edges. So each edge has an ID and a vertex 1 and a vertex 2 that they're connected to. Cool. I realize that is a little bit more complicated than, I think I've chosen quite a complicated example here, but this provides the information you need. It doesn't do it automatically for you because you want to be able to select the vertex type yourself. Is it a cage vertex? Is it a polymer vertex? This is important. And then we can write this, and if we visualize it, so cd tg output, and go pymol, I think it's all of them, you can see we have the cage underlying as sticks, and we can show the topology as, let's go dots. You can see the vertices are represented by those dots and the edges by the lines, and it overlaps with the building blocks of this cage. Obviously it does because it was a nicely defined example. Cool. I am going to stop this video here and see you next time. Thank you.